We're going to continue our work on rates of change, and we're going to look at a way of finding the gradient of the tangent to a curve at a particular point, and this will lead us towards the next video, which is about limits, and after that will be the derivative by first principles. So we're heading into our world of calculus gradually. So let's look at a simple example which illustrates the point of the video. So here we have an ugly drawing of y equals x squared. Okay, so we're going to start something fairly basic. It needs to be a curve, and we've got our x and y axes. You can see y equals x squared there, sketched in green. And let's say we've got the point 1, 1. So let's mark that on there. So 1, 1. That's an easy point to talk about. Let's call it point P. Let's say a bit further along the curve in some direction, I'm going to just choose to go up to the right. We have another point called Q. Now we could draw a chord between those two based on our previous work, and let's see if I can do that and it be visible. How's that? Is that alright? And we've got that there. From our previous work, we know that as Q starts to approach P, we get a better and better estimate for the gradient at point P. And to find that, we need to find the gradient of the tangent. The gradient of the tangent at P, which links to our previous work as well. Now, we've been able to do estimates in the past when we've looked at instantaneous rate of change. Here's another approach, and this will just touch the edge of a topic called limits. What we often do is call the gap between, in the x direction too, the gap between P and Q, this distance here. That's a variable, and we often call that h. Okay, it's a convention, so I'm going to do that as well. So that is h there, that gap. So all the way out to here will be, that distance will be 1 plus h, won't it? Because we've got the given 0.11. Now to get any y value, we just substitute our x values into the function, and this will mean that the point up here at Q will be able to be found in a certain way. So it'll be the point 1 plus h in the x direction, comma 1 plus h all squared, because we square it to get the y values. Now, because we're looking for the gradient of the tangent, we need to look at the gradient of this red line in general. So gradient is rise over run, or basically it'll be y2 take y1 over x2 take x1, delta y over delta x, whichever way you like to put it. So it'll be the difference between the y values over the difference between the x values. So we have 1 plus h all squared for the y value of point Q, minus 1 for the y value of point P, and we have the x value for point Q, x value for point P. And using our binomial expansion, we've got 1 squared plus 2 times 1 times h plus h squared minus 1 expanded out on the top. On the bottom we've just got h, which should be no surprise. You can see it there in orange. Oh, and I just noticed I forgot to write my squared there. Alright, so the ones on the numerator will cancel, and so we've got h squared plus 2h over h, divide top and bottom by a factor of h, and we have 2 plus h, or h plus 2. I'm going to write it as 2 plus h. It helps a little bit. Okay, a little bit of analysis now. So as this red line gets shorter and shorter as Q starts to approach P, h starts to get smaller and smaller. You can see that. So anything with h in it gets smaller, and as h approaches 0, something special happens. We have P and Q become the same point in a sense, and as h approaches 0, we have what's called the limit. It's an important word. Okay, limit of 2 plus h. So this provides, well, it provides a gradient because it's a gradient formula, isn't it? And this provides the gradient of a tangent at P. Alright, so we end up with a tangent at P. We don't have to draw it. So this is good that we don't have to try and draw it. Human beings can't draw perfect tangents without the aid of technology. So as h gets smaller and smaller, it eventually lands at 0, and so the gradient of the tangent at P, or the gradient at P, that's a P, equals 2. So basically that's as h approaches 0. Let's look at another example. So we've got y equals x squared minus 2x, and I've drawn another ugly sketch of it there. And we've got a given point 3, 3, and we want to know the gradient of the tangent at that point. Now we'll put in another point Q there, and so we basically look at the what would be the coordinates of Q. So I'll just write them over there. So if we use h again, it's 3 plus h. So the point coordinates for point Q will be 3 plus h for the x-coordinate, and 3 plus h all squared minus 2 times 3 plus h. So gradient So you could write that as gradient sub PQ. Gradient of PQ is the difference between the y's, so that's going to be 3 plus h all squared minus 2 outside of 3 plus h minus 3 over, well, the gap is called h again, but really in full it's 3 plus h minus 3, which obviously is h. Okay, so you have expanding the first set of brackets on the numerator, 9 plus 6h plus h squared minus 6 minus 2h minus 3 over h. Simplify, we get 4h plus h squared over h, and dividing through we get 4 plus h. So as h approaches 0, the gradient PQ approaches 4. Therefore, gradient of PQ has a limit of 4. Therefore, tangent at P has a gradient of 4.